Anyway, we have some Tizen reference devices here. We don't have enough devices to distribute all of you, but I guess maybe we are going to give you one device per session like that. Yeah. And yeah, we're just giving away them. They're free. So yeah, this session I'm going to present you about the Tizen memory management, especially in the kernel space. And it consists of three sections. The first one is Tizen overview, Tizen kernel overview. And the second one is memory management in Tizen kernel. So it's mainly about the memory management interfaces between user space and Tizen kernel. Basically, it's just a Linux kernel. And the third one is the memory size optimization techniques we have used in our Tizen reference kernel. Briefly saying, after doing some optimizations, including contiguous memory allocators and IOMMU, we have been reduced the reserved memory size to less than 1 megabyte. I mean 10 megabytes among 1 gigabyte of total memory size. And the free memory size was about 800 and some 40 or 50 megabytes among those 1 gigabytes of DRAM size. All right, starting with the kernel overview. Well, the Tizen architecture looks like this. I guess you have seen this before, but yeah, for kernel space and user space, it's quite obvious. Oh, sorry. And the kernel consists of these kind of major components in it. Well, the Linux kernel itself has more components, but when we try to make BSP for Tizen, these are the major components to be used or modified from the vanilla kernel. And there is another layer between the system core or system frameworks and kernel. It's OAR or OEM adaptation layer. It usually consists of many plugins between the kernel and user spaces. Some of the plugins are simple path or node definitions, and some others are more likely device drivers like OpenGL graphics backend. And in those major kernel components, the memory management related are these three ones: the memory management itself, and graphics, and then multimedia. Inside this kernel graphics and memory management, we are using DRM Jam and V4 to VB2. Those are kind of memory allocators in the graphics and multimedia. And then the DRM is supporting graphics output, like display, HDMI, virtual display, like wide-eye. And then V4 has codec, which is to decode and encode multimedia files, and then camera and radio. Okay, starting to the memory management in Tizen kernel. Yeah, let's start with basic memory management components. Yeah, so this DRM framework or direct rendering management framework has GEM or JAM for its memory allocator. And this basically allocates memory for the display. So when you are going to make buffers for the display or FIMD in Exynos or HDMI or other display-related components, you will usually make buffers via the JAM element. And unlike the Android or other ARM-based embedded systems, we are using DRM rather than just using frame buffers because they are more flexible, especially if you are going to use other external displays such as HDMI or the virtual displays. If you are using frame buffer with HDMI and virtual display, and if we are going to change the resolution or adding display space or changing the location relatively between the display devices, then the implementation may be too complex if you are just using frame buffers. And this is a simple layer between the DRM. And this GM, or Graphics Execution Manager, is a framework developed by Intel. It is usually, it was meant to be supporting the x86 devices. However, we found that this looked quite nice for ARM devices, and we have adapted the framework into the ARM devices, especially for Exynos 4 and Exynos 5 series. This is just general steps for usage of GEM. When you create buffers with GEM, and if we are using the standard APIs, then you will create a buffer without allocating actual physical memory. And this shows the steps for that. I will just skip them. However, when we are using Exynos or other ARM devices, we usually don't need that feature. And actually, if you are allocating memory spaces without allocating physical memory and then allocate each pages whenever you are demanding one, it will usually deteriorate the performance of ARM devices. Unlike x86, ARM devices are not that fast at allocating each page for each demand. So in our Exynos DRM driver, we usually use this kind of not on demand. It allocates all the physical pages when it is meant. When we are creating a GEM buffer. And if you are adapting to your own SoC, we actually recommend this kind of technique if we are using ARM SoCs. When you are sharing buffers that were made by GEM, this is the steps to share buffers between GEM devices. This GEM F-Link will create a shared buffer for other devices or other processes. And then this GEM open and close is done by other client or those who wanted to share a buffer that was made by other process. Anyway, these APIs are already in GEM framework, so you don't need to implement this. You just need to use this. And then another major component is V4L2, which is to support multimedia devices. And this V4L2 uses VB2, not GEM, to allocate memories. Well, this may look a bit not efficient because we are using two different memory allocators. However, the concept or the mechanism inside the frameworks are quite different from DRM and V4L2 because V4L2 usually uses streaming between the devices. Unlike DRM devices, if you are using, for example, a codec like MP4 or other video codecs, then it will continuously write frames automatically from the codec chips. So VB2 usually have more features than GEM, like controlling the streams or round buffers or other additional features than GEM. Well, if you look at the side above the kernel layer, you will see these GStreamer or OpenMax plugins. And as long as you provide these GStreamer plugins, Tizen will work. So, for example, if you are not using V4L2 and you still support any kind of GStreamer plugin, then the Tizen OS will work. But however, we recommend to use V4L2 for multimedia devices because its buffer management scheme, the VB2 supports the mechanism that we usually recommend, such as sharing buffers between GEM or other GPU-specific memory allocators. And there is another, it's not showing, yeah, this side. It's resolution problem?
Yeah, resolution here.
If you see this slide, we have GPU, and unlike those GPUs in x86, these GPU drivers usually don't use JAM or DRM. So usually these kind of drivers are ad hoc devices, ad hoc drivers, and it does not support JAM or VB2. So they usually use their own memory management techniques, and they are usually not compatible with Tizen. However, as long as you support the DMABUF to share with other frameworks, then it should work. So as long as you support that feature, the GPU will work with Tizen. Okay, going to next, purpose sharing. So again, yeah, this is the situation where we need something to share purpose between the memory management components. For example, here in this example, camera fetches a video stream from a camera, and then X server or EFL application will create a UI for the display, and the GPU will merge the two images from the user space application and then a camera and send the merge the image to display. Yeah, it throws its own image, and then GPU merges the two and puts the image to the display. However, the problem is that the components here uses different memory management techniques. So the data is not compatible with each other. For example, the buffer from camera uses VB2, and the GPU is using its own mechanism. If you are using Mali, then it's using UMP. And then the display uses yet another buffer management. So they are not compatible. However, if we add this component, DMABUF from unified memory management, then you can make the buffers compatible with each other. We can export to DMABUF from VB2 or JAM, and then share them between them. Yeah, we have added DMABUF to this. All the features described in previous slides are already upstreamed, so you don't need to add patches for these kind of mechanisms. Using DMABUF, you can export or import. Export means you are converting the object into DMABUF, and import means you are converting the DMABUF into your own object. User space will use DMABUF as file descriptor, so it is dealt as a single file. So you can just send the file to another user space processes, then it can use the shared buffer, and it may import that shared DMABUF object into its own memory management. And this is another scenario using the camera. Here, we are sending images from camera to user space programs, and then it will send to the display. I'm going to show you how the Tizen works with this kind of scenario. So at first, the camera will allocate memory via VB2. And the red box on the right-hand side is the memory buffer allocated via the VPL2. So it has created a buffer. And then the image comes from the camera to the buffer allocated. And then the image is exported to DMABUF by the camera application so that it can be shared with other components or other processes. So it has created file descriptor now. And then this file descriptor is then imported to JAM buffer so that it is converted as a JAM object. And then this is sent to the X server, and X server shows the image to the display. So although the camera uses VPL2, VB2, and display uses DRM JAM, this image is copied or shared with the display without any memcopy operations. Yeah, this is the final step of it. And then deallocating or freeing the memory buffer is completed if all the shared processes have freed its links. So at first, the X server frees the gem object and removing the link. And then this camera applications removes the DMABUF, and then it will be freed from the memory. However, going back to DRM gem, and in the current version of Linux, does not have DMABUF import or export feature in DRM gem. So in order to use this feature in your Tizen devices, you need to implement DRM import and export into your DRM drivers. And in the Exynos DRM drivers in mainline or the Tizen reference kernels, you can see the example at the Exynos prime DRM prime drivers. So, and then I'm going to describe a bit about the buffer allocations. So with the unified memory management, we have used DMABUF sharing buffer, and then we have used the same UMM for allocating buffers via the standard framework. The DMA mapping APIs is to allocate memory chunks or buffers for DMA devices, and it includes CMA, Contiguous Memory Allocator, and IOMMUs. Well, CMA has been developed in Samsung for like 2 or 3 years, since 2 or 3 years ago, and then it has been merged to mainline. CMA allocates physical continuous memory for the DMA devices without IOMMUs. And well, IOMMUs is obviously to support IOMMU devices, which has MMUs in the IO devices. So this is an abstract example in Exynos kernel drivers. So with this DMA mapping framework, it supports CMA and IOMMU. And the IOMMU requires a driver specific to its own SoC. So if you are using like Freescale, then you need Freescale IOMMU drivers. If you are using Exynos, then you need Exynos IOMMU drivers. In our implementation, we have several DRM drivers like display, HDMI, virtual display, or image post-processing. However, for the memory mapping, we have a unified memory management driver so that each device can share the address space. This has accelerated the memory management processes in the DRM drivers. However, in V4L2 drivers, we have not yet unified the address space or memory management. Well, if we have unified them, then the operations in V4L2 may be accelerated. But however, in the mainline drivers, we have not yet done it yet. And there's another problem with memory management in the Tizen. Well, this is kind of common problem with other operating systems such as iOS or Android. Well, yeah, we have a huge problem. And we have, as you have seen in previous slides, we have different entities to access memories in Tizen. For example, in this example, we are trying to access memory at the GPU, display, codec, and user space. Here is an example where we have issues with synchronization. Well, in this example, the process writes to buffer 1. Here, GPU means a user process or any arbitrary process in CPU. And then CPU tells GPU to do something on buffer 2, buffer 1. Like if you have written some images in the memory and request some transformations or other operations to GPU, and GPU does something on that buffer after having some operations, and GPU finishes. And then we are supposed to read the buffer 1 at CPU. However, without any synchronization method, CPU may try to read this buffer 1 while GPU is writing. And then we will get some fragmented or broken images on the display devices. Yeah, this is quite common issue or common bugs at Tizen kernel in the previous versions. Well, in the release versions, we don't have any bugs like that, but in the development, we have suffered from this kind of bugs. Yeah, we need a mechanism to ensure some synchronization between the GPU and CPU. However, this does not end with this scenario. If we have different threads or processes in CPU that are going to access the same GPU, then we get more problems with the synchronization. And yet another, we have other DMA devices. Like here is image post-processing, and then we have HDMI or G2D accelerator, and many others DMA devices, and they may access to the same buffer at the same time. So we need some kind of synchronization method between them. And in Tizen 1 or Tizen 2, we have been using Tizen global lock, which is simply a shared mutex between the processes and device drivers. And we let user space handle this issue with this lock. But however, we need some improvement in here. Usually, global lock is not recommended because of the performance issues. And in order to use this feature, you need a kernel patch. Well, this is kind of limited or restrict. This is only for the Exynos reference devices, and you may have your own implementation in your own SoC. However, yet we do not support any mechanism to support this issue in general. However, in other systems, like in Android, they are using Sync framework, but they are not using DMABUF. So, and the resources are not yet managed quite well in Android. So this is quite similar with Tizen global lock. However, Android is a bit more performing better in this area. Yeah, and we have tested with KDS. However, this is already became obsolete, and we are testing with DMFN's framework. And I guess this is the way that Tizen will go in next few months. And we have tested with DMFNs, and the test has been quite successful. Yeah. So I guess the next Tizen will use DMFNs, and by using DMFNs, we have shown that the performance is quite upgraded. For example, in the same hardware, same platform software, by adding DMFNs, we have improved like 40 frames per second to like 50 frames per second. And on an example with 55 frames per second, it has been improved to 60 frames per second. So yeah, DMFN seems to be quite nice, and we are going to use it. Yeah, and this is I'm going to present some example optimization method we have been using for the Tizen devices. For reference, we are using Exynos 4210 and 4412. So we have two devices, and both of them have 1 GB of DRAM. Yeah, there is another device with 500 megabytes of RAM. Unfortunately, the multimedia devices want to use 400 megabytes reserved. So we have only 1 megabyte to use. Well, somehow we have optimized the Tizen platform to work on this environment with only 100 megabytes. However, later they wanted to use web browser in this system. And this web browser needed to run the web applications. So there is no way to run web application with 1 megabyte of free memory. 1 megabyte is shared with kernel and other middleware and all the other daemons. So the web browser didn't have memory to, like, it had less than 40 or 30 megabytes. Well, we were tasked to solve this, and in conclusion, we have successfully landed the web browser and web application in this environment. What we did is using CMA. This device didn't have any IOMMU devices. Well, it's quite primitive, but it was used to lower down the cost. And most of the 5 megabytes of reserve memory was used by the camera. The camera was required to have like 10 sequential shots. So when you are web browsing, you usually don't use cameras. So we can use the reserve memory for camera while web browsing. So with CMA, we can free all the reserve memory for cameras. So we can use that for web browsers. And when the camera is on and it tries to reserve these 400 megabytes, then it will migrate the memory if there is a free space in the out of the 400 megabytes. And if there is no enough spaces, then the web browser will be killed. And this is the architecture of the primitive, the 500 megabytes of DRAM. And what if we have IOMMUs in GPU? Then we can use sort of virtual memory like memory management for the DMA devices. And if we can use the IOMMUs at DMA devices, then we can dynamically allocate and free the memory. Well, with CMAs, we somewhat dynamically allocate and free, but it is quite limited. Like, it does not support any paging, and we cannot allocate and free frequently with CMA because it requires migration to allocate the physically continuous memory addresses. So with CMAs, we still have some spaces wasted. However, with IOMMUs, it's like just using virtual memory at usual processes, so it's quite efficient. With this IOMMU system, in Tizen, we could make the display and GPU to use less than 40 megabytes and achieve near zero reserve memory. However, in the Tizen reference kernel, or this reference devices does not have this one. This IOMMU is only in the development kernel and will be released later. Yeah, this is the example output of Tizen kernel. With these IOMMUs, you can see that the free memory here, this one, we have like about 850 megabytes free. So we only use 150 1 gigabytes. So yeah, it was quite efficient. The reason why we have tested with 500 megabytes is because we wanted to show that Tizen could be used for low-budget devices. And I guess with enough optimization in the middleware and user space processes, I guess we can use with like 300 megabytes devices could be used. Well, I haven't tried it yet, but it's my field guess. And another issue with memory size is about the multitasking or background apps. If you allow to use multitasking or background apps running while the foreground application is running, then these background or multitask processes will consume the memory. If you want to use for low-budget devices, then I guess you need to limit or restrict any background applications. And there's another technique to optimize the memory size. This has been used for Galaxy S3, and I guess it was also used for Galaxy Note. but I'm not sure about the node. This DRAM feature creates a swap space in DRAM. It makes swap space at RAM disk. So it looks quite stupid, but it compresses the swap space so that it can it may have more storage in the RAM devices. I guess they have about 100 or 150 megabytes in the swap space, and they could enlarge a bit in the memory size. Or even we may imagine to use the conventional swap to storage in mobile devices. We have some limitations in the ARM devices with flash memory, but with the recent devices like eMMC 4.5 or eMMC 5 or even UFS, I think it's possible to use swap to storage. Okay, for the multitasking and background apps, the first one is quite obvious, just limiting the number of multitask or background apps. And the second one is pseudo multitasking. It's used by iOS. iOS usually freezes the background apps to the storage, and it frees all the memory used by the background apps. And if you have limited DRAM, this might be one of possible solutions for that. Okay, any questions or comments? Is there any product that has been successfully using CMA? Well, I'd say yes. There are devices using CMA devices, and they haven't released, like the cameras. Some of Samsung cameras are using CMA.
Isn't there any problem about latency?
There is problem with latency, the migration latency, but for those products, it was acceptable. Swap, printers. Printers use swap. Yeah. Printers usually have small size of DRAM. However, they have much data, like the PDFs going in, and they use swap.
And as far as I know, CMA cannot make sure locate always because the driver can pin some page.
Right, that's an issue.
Yeah.
So you need to carefully design your own device drivers so that it won't take places in the CMA region. So there is a tool to find out who's pinning down in the CMA allocations. So you can find out which driver is doing that. All right. Any other questions? Okay. You can just contact me personally for any other questions, or you can send me an email. All right. Thank you.